Good morning everyone, this is Dr. Alex Crespo. I'm going to present this work that has been done in collaboration between different universities, my university, University of Vigo in Spain, the UPC in Barcelona, and the University of Salerno. Also, I would like to highlight that this work I'm presenting today is part of the PhD work of Pablo Ropero Giralda. Let's start first with the motivation of this work. We are going to focus on developing a numerical tool because we believe that this can help in the design stage of WECs. We aim to develop a robust numerical tool to simulate WECs that we are going to validate with experiments, and the numerical code can be used to study not only the efficiency but also the survivability of the device under extreme wave conditions. This will be the outline of my talk. Let's start now with the WEC in particular we are going to study here. In this figure you can see the distribution of research efforts according to the different technologies, and the 40% is focused on point absorber. A point absorber is a floating buoy, and in this case will be only heaving buoy that is oscillating on the surface, and connected to the bottom we can have a power takeoff system defined as spring as a damper. Let's now talk a bit about numerical modeling of WECs. So here you can see two different approaches. The first one is based on the linear potential flow, where we are going to use boundary element method. These methods are fast and efficient, but they cannot deal with viscous forces, and they can only be applied to study small amplitudes. Some examples are WOMIT, WADAM, NEMO, WEC-CIM. On the other hand, we have computational fluid dynamics, where we are going to solve the Navier-Stokes equations for the whole velocity field. They are time consuming, but they can simulate no linear flows, viscous flows, and they can deal with violent impacts. We can here have two different types of CFD, some of them based on a mesh and other ones meshless. The mesh-based methods are the more conventional and robust that have been applied for years in problems of fluid, such as OpenFOAM, IHFOAM, Fluinco, RIF3D, and many others. And among the meshless methods, which are novel, we have a smooth particle hydrodynamics, that is SPH. In the SPH methodology, the fluid is represented using particles. The particles will move according to some governing equations. In this case, according to the Navier-Stokes equations. So the main idea is, considering a particle of interest I, this particle is another point where physical quantities are computed as an interpolation of the values of the neighboring particles. Here, if we want to compute the magnitude A of this particle I, we are going to use the values of A of the particle J, and this contribution is measured using a weighted function or a kernel function. So the main idea is to solve the mass conservation and the momentum conservation that will be rewriting a discrete form using summations. So during the SPH method, we are obtaining density, velocity, and position for each particle, and the pressure in this case is going to be obtained using equation of state, because we are going to be using a weakly compressible approach. Then, just to say something about the boundary conditions, this is still an open problem in SPH. We have different approaches. The well-known ghost and dummy particles. We can use repulsive boundaries, or we can use dynamic boundaries. In the case of dynamic boundaries, what we are going to do is we are going to discretize the boundary as a set of particles. If we want to simulate a rigid floating body, we will use the same technique, the dynamic boundaries. In this case, we will obtain the force exerted by the fluid on each particle of the floating body, and together with the weight of the whole floating body, we can solve the equations of the dynamics of a rigid body to define the velocity and position. Here you can see an example of a dam break impacting an obstacle, and as you can see, I'm plotting particles and the color corresponds to velocity. On the right, we can see how the particles move propagating waves which are interacting with floating boxes. Here the boxes are represented by planes, but in fact they are a set of particles moving of a rigid floating body as mentioned before. So there are several advantages of SPH comparing with mesh-based codes, like the efficient treatment of large deformations. There is no mesh distortion because there is no mesh, so no need for a special treatment of the phase surface. We can handle complex geometries, we can deal with multi-phase flows easily, and we can add external forces or different discontinuities. And the drawbacks are that boundary conditions and turbulence are still an open field, so more research is needed there, and the time computation is very expensive. Here you can see another example. This is an application of waves interacting with a breakwater. So this problem is being here solved by SPH. You can see here the trajectory of the particles, but it could be solved by a mesh-based code for sure. In the case of mesh-based code, we only have to define initial and accurate mesh. So there is no need to use a meshless code here. However, in this second example, where we are simulating debris flows, what we have is rocks interacting with other rocks and interacting with the fluid. So this, in terms of a mesh-based code, will be really difficult because the remeshing and the mesh distortion that we can obtain here will be impossible to solve. However, using a meshless approach, this is almost straightforward. So can this problem be simulated with mesh-based methods nowadays? I would say that now in practice it's not possible, but with SPH it is. Let's move now to a description of an SPH code in particular called Dualis Physics. Dualis Physics is an open source code available for free on the website. It has been downloaded not only for people from university, but also from companies. In fact, a lot of wave energy companies have shown interest on that, and they have downloaded the code. It's a collaborative project where we work together, the University of Vigo in Spain, Manchester, United Kingdom, the IST here in Lisbon, also the University of Parma in Italy, institutions from Belgium, and the Institute of Technology in New Jersey from the US. We release the code as GPL with GPL license and also LGPL. It's highly parallelized, can be executed not only on CPUs but also on GPUs, which are graphics card, where we can get the speed ups of the order of 100 times faster. It includes pre and post processing tools. In fact, we have a graphical user interface and also advanced visualization using FreeCAD and Blender respectively, which are also open source. And the idea of Dualis Physics is to use SPH to simulate real problems. In addition, we have coupled Dualis Physics with Project Chrono. Project Chrono is an open source multi-physics simulation engine that includes joints, a lot of constraints, friction models, springs and dampers. And springs and dampers is what we are going to use to simulate the numerical behavior of the PTO of the WEC. So this opens the possibility to simulate many different applications. Here on the right, you can see a oscillating wave surge converter, which is a flap hinge to the bottom, and this hinge is simulated using Chrono. Let's focus now on the results with the point absorber. First, the validation. We have followed the example that the experiment described in the paper of Sang et al., where we have a heaving-buoy connected to a rod with a PTO also attached to the bottom here. Here you can see the dimensions of the buoy, and we are going to reproduce these regular waves. The behavior of the PTO will be simulated numerically with Chrono. In the end, all these examples are using zero stiffness, so what we have is different damping. So we are going to simulate this as a damper. This will be the numerical domain, where our WEC is located at one wavelength from the piston. Then we have a dissipative beach and also a numerical damping or sponge to avoid reflected waves. And the width of the tank is only 2 times the diameter. This is not enough, but we are using also here periodic boundaries instead of lateral walls, and we are using also here some sponge layers. Here you can see the result of the simulation of these regular waves interacting with the WEC for different damping coefficients. And here you can see the runtime to have an idea. Simulating 15 seconds of physical time took almost more than 30 minutes if we are using a higher resolution. Here you can see the number of particles, almost 7 billion particles, using different resolutions. If we compare the numerical results with experiments, we obtain these figures about the heave motion, vertical velocity. Blue and red are different resolutions for the numerical results. The black is the experimental one, and we can see that for different damping coefficients we get a nice agreement. So we are going to continue using the coarse resolution because the accuracy is good enough and we don't have to spend 30 minutes running. Just some minutes will be enough to get the results. So let's move now to the efficiency analysis. We can do efficiency analysis simulating different wave conditions. In this case, we are going to use different wave periods, same wave height as before, for the different BTO damping coefficients. So you can see here the list of all the different periods. We are going to define the efficiency as the power absorbed by the point absorber divided by the wave power of the wavefront using the capture width ratio. Or we can use the capture width ratio divided by the maximum capture width ratio. That's the same. I'm going to use this in the figures, but we could have used this value, of course. So here we can see the variations of absorbed power with the frequency of regular waves for different values of the damping. The figure in the left shows the maximum absorbed power that occurs at around frequency divided by natural frequency equal to 0.5 for the higher damping coefficient of 1100 and around 0.8 for the lower damping coefficient. The peak of the power absorbed tends to appear at frequencies close to the natural frequency as the damping coefficient of the BTO decreases. A similar behavior is observed in the figure of the right for the efficiency, defined here as I said before. But in this case, the peak of the efficiency takes place at frequencies slightly lower than the natural frequency for all the values of the BTO. Let's now move to the survivability study. So, the survivability of the WEC is analyzed at a location in the north coast of Spain, 4 kilometers offshore from the port of Ghent, where the water depth is 54 meters. Well, in practice, 1000 waves are employed to represent the real sea states when reproduced experimentally. Here, with numerical models based on Navier-Stokes equations, either mesh-based or meshless, must often cope with huge computational costs associated with such long test durations, especially for 3D modeling. Therefore, instead of a full sea state, a focus wave group is simulated here. Here I am defining different parameters, but let's consider a lifetime of 20 years and an exceedance probability of 0.53 corresponding to the damage limitation limit state. So a design wave height of almost 1 meter and peak period of 5.30 seconds are obtained using the Freud scaling to the scale of the system we were studying before. In the present work, a unidirectional crest focus wave, defined according to the so-called new wave method, is employed. The new wave linear theory developed by Trommans et al. Defines the free surface elevation in this way. The generation and propagation of the focus wave at a desired focus location is validated first running a 2D simulation without the work. So the focus wave is generated using this height, period and depth, all of them already scaled, and the free surface elevation measured numerically with Dualis Physics at a focus location of 15 meters is compared with the second order analytical solution, and the agreement is good. Here we can observe the lateral view of the 3D numerical tanks we are going to employ in this survivability study. The midpoint of the WEC is at 15 meters, which is the focus position, and 6 different cases are going to be considered. In all of them, the PTO is not working, so we are not using chrono here. The different survival strategies are defined considering the effects of submerging the device and simulating the WEC fixed or oscillating. In the next figures, we are going to show the forces along with the theoretical time series of the free surface. For the sake of clarity, it's split in two figures. On the left are the cases with heave motion, and on the right the cases where the device is fixed. So let's start with this horizontal or longitudinal direction of the force. Here we can see how this Fx horizontal force follows the trend of the free surface elevation. In fact, the maximum values of the horizontal force take place during the peaks of the elevation time series. Fully submerging the buoy reduces the maximum amplitude of Fx, since it's lower for the cases B and C than A, as we can see in both figures. Comparing at the same depth, the magnitude of force is lower when the device is fixed. However, the effect of holding the device fixed is minimized significantly when the WEC is completely submerged. In this case, we can see the forces in the Z direction, or they oscillate around zero when the device is fixed at the still water level, and they oscillate around this value, which is the weight of the buoy when they are submerged. The values of the vertical force are very similar for the cases when the device is completely submerged, regardless of whether it remains fixed or oscillates. However, comparing the results of the vertical force for the heaving and fixed device initially semi-submerged, a great difference can be observed. As a matter of fact, configuration A1 minimizes the vertical force, while configuration A2 maximizes it. The analysis of the force alone does not clearly determine the best and worst case scenario. Thus, a criterion that takes into account both contributions is needed. The structure considered in this work is a simplification of the experimental of Zhang et al., which assume that the buoy is connected to the seabed by means of a clamped rod of circular cross-section. So, it's possible to characterize the effects of the wave field on the buoy and its structure by performing what we call an elastic verification based on the yield criterion defined in this reference. So, if the value of the yield criterion is higher than 1, indicates a failure of the structure. Here we can see the contribution of the two forces and the definition of the rest of the parameters. So the time series of the yield criterion of each scenario are obtained assuming a rod made of steel and for different values of the diameter of the rod. And here you can see the maximum values in this table. If the diameter of the rod is 14 millimeters, the buoy is heaving at the still water level, the maximum value of the yield criterion is very close to 1, and therefore the structure of the WEC could collapse under the string event considered here. To avoid this, three strategies are studied: fixing the device, submerging the buoy, and increasing the rod diameter of the structure. The main conclusions are the most effective strategy to reduce the wave-induced effects is to submerge the device. Submerging the device even more is not really improving the results and will be associated with higher costs. Fixing the device, which is the case V2, reduces slightly the maximum yield criterion with respect to the heaving device. Thus, the cost and reliability of the mechanical system needed in each case should be considered when making that choice. Now let's move on for conclusions and future work. The hydrodynamic response of a point absorber under regular waves can be accurately obtained with Dualis Physics. We have validated numerical results for different configurations of the PTO system for a given regular wave condition, and once the tool has been validated, we have applied for efficiency and survivability study, survivability under extreme wave conditions using focus wave, and our next steps now will be to do a survivability study, including also economic factors or environmental impact. And in terms of new functionalities in the code, there is a module of Project Chrono that will allow us to simulate the rigid structure of the buoy as a flexible structure, which we think that can increase the lifetime. Thanks a lot for your attention.